Um, Now this is interesting. Later in development, new experiences can cause neurons to secrete neurotrophins. Increased branching of axons help store memories. I'm going to be showing you a video in a minute of the nun study, where basically what have is this: they have this convent of nuns, and they all live to be well over 90, and they all donate their brains to science, which is so kind of them. But all of these nuns, they stay very active. They teach until the day that they die. They play Jeopardy every night on television. They get up every morning and they exercise by walking around the track. They constantly keep themselves mentally stimulated. Like, the only TV that they even watch is Jeopardy. Basically what they found is that when you look at their brains as opposed to people who have succumbed to Alzheimer's disease, basically their brains look the same, because what you see is the wrinkling. The wrinkling has kind of pulled apart. There's big spaces between the wrinkles. And so you'll see that they've lost the same amount of neurons. They have the same atrophy of the brain, where the brain is shrunk through age, like in Alzheimer's. But what they think is they think by them constantly trying to learn new things and becoming mentally stimulated, that even though they've had a lot of neuronal loss, their other neurons have developed more branches to compensate for the neuronal loss, so they don't show the memory impairments that Alzheimer's patients have. So something that really is healthy for your brain, is healthy for your body, is exercise. Exercise releases the neurotrophins. So this is something from your Psych 1. Now, you don't have to have taken Psych 1, so if you never did, don't worry about it. But in Psych 1, they learn about this theory, Piaget's theory of cognitive development. And the first 2 years of life, he says basically, he calls it the sensory motor, and he says that basically at this time in life, the children are developing connections between the sensory and the motor neurons. And so this is a time period we're going to get to. The next place is called television in the brain. That's going to be our next module. And basically the American Pediatric Association says absolutely no TV for children under the age of 2. Now, I'm going to be so honest with you, and it's embarrassing honest, is, you know what, the TV in my house is on probably 24 hours a day. Now, they're not watching it all the time, but, you know, I have a little one. He's 3. That's the youngest one. And he just seems to always want to turn it on. And then if you turn it off, it's just like this massive fight. And I can only deal with so many massive fights a day. So usually I end up just turning it on, and then they're all running around the house. So I know that for some of you that have little children, you know, it's very hard to keep the TV off. But I think also we should be aware, like I feel bad all the time when I see them just watching TV, but I also know that for me as a person, I have to balance, like, how much can I do and force them to do, and how much do I need time just to have a conversation, just to be recording this lecture, just to have a little bit of sanity. So a lot of us use the television as a babysitter because it's different than it was in my generation. In my generation, we went outside and we played all day from morning up till dark at night. You had to come back when the street lights go on, and the parents had their break that way. But in this time period, basically the children can't go out and play unsupervised. You can't just send them down the street to the neighbors. There has to be lots of supervision. And so what we use instead is television. But I probably it would be better if we can get them out exercising. We'll get to the television in the brain a little bit later, a little bit more. But what you guys are doing here by becoming educated is you're developing longer and more widely branched dendrites. By forcing yourself to learn new things, your brain is becoming more diverse. I always ask my students in my classes, I'm like, if you had an employee, would you rather hire an employee with just one street, like a small town brain that's got one street and there's only a couple ways to go, or would you rather hire somebody who has a big city brain that has lots and lots of freeways all over? Okay, so this is the brain structure of a newborn. See this, remember that 350 grams? And then I said, look, they add about 650 grams, you know, by the age of 1. So in 6 months, look at this, lots and lots. And then 2 years, look at this. That's what you're doing throughout life, is you're adding new dendrites.
And people keep asking, well, what is old age?
Right, right.
And I say it depends on what part of the body.
Right.
Because development and aging are a continuum through a lifetime.
Right. Now 73, Dr. Marian Diamond has been challenging herself all her life. She is internationally recognized for her groundbreaking research on the brain. She has also been honored as one of the nation's most distinguished teachers. Two of her accomplishments as a researcher have earned her particular recognition: her work on the structure and differences between male and female brains, and her discovery that with proper stimulation, brains continue to develop at any age.
We wanted to know, well, what's going on in the brain? 12 rats in a large cage with lots of objects to play with. And in contrast, there was one rat in a single cage. And they stayed in their environmental conditions for 80 days. And at the end of 80 days, we looked at the brains. And the chemist looked at the chemistry, and I looked at the anatomy, and found that the cerebral cortex, the outer layers of the brain, had changed by 6%. There was a difference between the enriched and impoverished. This German professor stood up at the back of the room and he said, "Young lady, those brains are not old. Our German rats live to be 800 days. So we came back to Berkeley to figure out how we're going to get our rats to live long, because we were actually losing them at 600 days, and that's why we decided to use them at that age. And so we decided to give our rats TLC. Well, we took them and held them against our lab coats and talked to them for a few minutes each day, and we found the 904, which as far as we could calculate is equivalent to a 90-year-old person, we were still seeing the changes. So that let us know that we could change the young brain, as everybody anticipated, the middle-aged brain, and I've never seen the Germans come out with older rats than 900. In fact, my colleagues all say, "How did you do it?" But I don't think they're willing to give the TLC that's necessary for these long experiments. And that's why we don't have so much data on the older animals as we do on young animals. Well, we haven't talked too much about what is changing in the brain. These are the cerebral hemispheres, and they're covered with a few millimeters of nerve cells right beneath the surface. And that structure is called the cerebral cortex. Humans have association cortex. So things come in and then go to association cortex. And recently it's been shown that new neurons are developing. Things that they've learned about Alzheimer are the
enormous interest now in what the effects of lifestyle interventions such as exercise and diet may have on the risk for Alzheimer's disease or on brain health and function in general. In animal models, mouse models of Alzheimer's disease, for example, there is recent evidence suggesting that exercise and diet can modify the progression of the lesions of Alzheimer's disease in these animal models.
One of the breakthroughs in the field is to be able to have a mouse model of Alzheimer's disease called a transgenic mouse. And it simulates a lot of the pathology that develops in the human brain with Alzheimer's disease. I had this idea that maybe a growth factor or a neurotrophic factor, which is kind of a nutrient or a fertilizer to neurons, which also makes them smarter, might be naturally increased with exercise. We take two groups. One is just sort of in their cage and don't have access to a sort of a running gym. And the others get in their running wheels at night and they exercise. In order to test their learning, we basically take the two groups and put them in this Morris water maze. They are put in the tank and they don't like the water. And what they have to do is they have to find a little platform. It's sort of below the surface. It's really kind of equivalent to finding your car in a parking lot at an airport when you can't really see it, but you sort of have to learn from the cues around the airport of where you parked.
The sedentary animal still has not located the platform at this point.
All right.
We find consistently that the animals that have exercised are able to learn faster and better than the animals that haven't exercised.
All right.
Yay!
Did it?
We looked at their brain, and lo and behold, BDNF was increased in the part of the brain that is controlling thinking and learning and is vulnerable to Alzheimer's disease. And all I could say to myself, and my students would say, holy camoli, that is so smart. The brain knew something and how to look out for itself that we had no idea about. So it kind of has a self-preservation mechanism that also makes it smarter and to learn better. Certainly in animal models, there's no question about it. Exercise